So we started this unit with just a review of some of the things that you should have learned in physical science about solutions. We start off by looking at the three different types of mixtures. A mixture is a physical combination of two or more pure substances. So we take two or more elements or compounds, and we combine them together, basically putting them in the same place at the same time. They are physical, which means that there are no new substances formed when you make a mixture. So, for example, when you mix salt and water together to make salt water, it's still just salt and water. You have the two things in the same place at the same time, and that's really all a mixture is. Those mixtures can be classified into three different types: suspensions, colloids, and solutions. The suspension is a heterogeneous mixture, which means it's the type that doesn't mix evenly. The particles are often large enough to see with the naked eye. So, for example, if you take a look at muddy water up close, you could actually see little tiny things floating around in it. Because those particles are so big, gravity has no problem grabbing those particles and pulling them down to the bottom of the container. So these types of mixtures do settle relatively quickly. They include things like muddy water, oil and water, Italian salad dressing, and even soil. In all of those, you can see the individual different parts. In the liquid ones, it's easier to see the settling thing, but even if you took soil and it was loose enough in a bucket and shook it up, the heavier stuff would fall to the bottom and the lighter stuff would stay at the top. Colloids are the second type of mixture. They are also heterogeneous, which means that they're very much like the suspensions. You have stuff that's literally suspended or floating around in your mixture. But this time, rather than the particles being big enough to see with the naked eye, they are microscopic. So we're breaking this down to a microscopic level. Because these particles are so small, gravity does have a very difficult time separating them. So they may never separate, or they will separate extremely slowly. Examples of these include paint, mayonnaise, fog, smoke, and milk. And each of these, if you think about them, has kind of a milky white color. Paint comes out of the factory white. When you want red paint for a wall, you have to have them tint that paint to whatever color you want. Typically, it's a milky white color. All of these things have a milky white color because of the Tyndall effect. You might not be able to see the particles that are in this mixture, but the particles are large enough to scatter light. And it's that scattering of light that gives them that milky white color. In our picture down here, this first glass has a solution in it, and the light just passes through like there's nothing there. In our second one, we have a colloid. You can see how it has that milky white color because of the scattering of light. This first one has a solution in it, and that light passes straight through that solution because of the size of the particles. Solutions are our homogeneous one. That means they do mix evenly. The particles cannot be seen even with a microscope. They're broken down on the ionic, atomic, or molecular level. They are down to the size of atoms and molecules. So even with a microscope, you wouldn't be able to see the individual particles in a solution. They will never settle or separate simply because the particles are just way too small for gravity to even affect them. Examples of these include saltwater, rubbing alcohol, and alloys like stainless steel, brass, etc. A solution contains two parts. They are called the solute and the solvent. The solute is what is dissolved. The solvent is what it is dissolved in. So in the case of salt and water, the salt is what is actually dissolved. It's what disappears when you make your solution. The solvent is the water. That is what it is going to be dissolved in. Now, when there is true dissolving, it is easy to decide what the solute and solvent is because of those very definitions. When nothing is being dissolved, as in the case of mixing two liquids or dissolving a gas into a liquid, those definitions become a little harder to use, and what you have to do in those cases is look and see which one you have more of. The one you have more of is the solvent. So we're talking about putting food coloring in water. I mean, nothing's really being dissolved. The food coloring is a liquid, the water is the liquid. You're just mixing the two liquids together. You will definitely have much less food coloring than water, though, because you have more of the water. The water is the solvent. Because you have less of the food coloring is the solute. I mean, this can be kind of tricky if you think about it. Rubbing alcohol, for example, you can buy different concentrations of rubbing alcohol. You can buy solutions that are 40% rubbing alcohol. You can buy solutions that are 90% rubbing alcohol. And what you would call the solute and solvent would be different in both of those cases. In the 40% rubbing alcohol, the water is the solvent because it is 60% water. You have more water. But in the 90% rubbing alcohol, the isopropyl alcohol is the solvent because you have more of it. So we have two different definitions because there are honestly a wide variety of solutions, and you have to have different definitions to suit the different types. If there is true dissolving taking place, if something is disappearing from a solid state, use the first set of definitions. If you're mixing two liquids together or talking about dissolving a gas into a liquid, use the second ones. Solutions can be classified as being either electrolytes or non-electrolytes. It just depends on if you have ionic solutes or covalent solutes. If your solute is ionic, then it is an electrolyte solution. These ionic compounds will break down in a process called dissociation that will break those ionic solutes down into individual ions, positive and negative ions. Those ions will conduct electricity. That's why it's called an electrolyte solution. Salt water is a great example of an electrolyte solution. Again, in the non-electrolyte solutions, the only difference is your solute is covalent. So when you dissolve it, it won't break down into ions. It'll break down into molecules. There will not be charges. And because there's no charges, they don't conduct electricity. So it is non-electrolyte. Sugar water would be an example of a non-electrolyte solution. So electrolyte just simply refers to whether or not there's ions there. To have ions there, you would have to have an ionic compound like sodium chloride as your solute. Solubility, that's the limit to how much solute can be dissolved in a given amount of solvent. There is a limit to how much salt you can dissolve in water. There is a limit to how much sugar you can dissolve in water. And that limit is called its solubility. It's expressed as grams of solute per 100 grams or 100 milliliters of solvent. For water, it can be grams or milliliters because they are the same. 100 grams of water is the same as 100 milliliters of water. What you see on the screen is the solubility of sodium chloride, table salt. It is 36 grams of table salt per 100 milliliters or grams of water. In other words, you can dissolve exactly 36 grams of sodium chloride in 100 milliliters of water, no more. That is the limit. If you try to put in 36.5 grams of sodium chloride, the extra half a gram isn't going to dissolve. The extra half a gram would just settle to the bottom and sit there. Now note the solubility is written as being at 20 degrees Celsius. That implies temperature will affect solubility. Saturation is a description of a solution that's relative to the amount of solute it has as compared to the solubility limit. An unsaturated solution is one that is below the solubility limit, one that has less solute than what it could possibly hold. Because it's below the limit, if you add more solute to it, that solute will dissolve away. It will go into the solution, no problem. You can continue to dissolve solute until it becomes a saturated solution. Once the solution becomes saturated, then you can't dissolve anymore. And any more solute that you add will just settle to the bottom and it won't dissolve. It'll just sit there. If you have a solution that is beyond the limit, you call that a supersaturated solution. And again, now you're probably thinking, well, how do you get above the limit? If I add any solute to a saturated solution, it's just going to settle to the bottom. How do you get more to dissolve? Well, that's where that 20 degrees Celsius thing comes in, the temperature. You have to manipulate temperature to make a supersaturated solution. That's coming up on the next slide. If you add more solute to a supersaturated solution, Again, it will just settle out, but this time it may act as a seed that allows the extra solute that is in your solution to precipitate out or to crystallize out. There are factors that will change the solubility. Temperature is indeed one of them. If you're talking about gases, there are actually two. Increasing the temperature of the solvent will actually decrease the solubility of a gas. So the hotter the solvent is, the less gas you can dissolve in it. In class, we talked about a phenomenon that you often see around little ponds and lakes in the summertime. Oftentimes when it's summer and it's really hot outside, you're walking around the banks of a pond, you'll see dead fish on the banks of the pond. Those dead fish have suffocated. As the temperature of the pond water has increased, the amount of oxygen that pond water can carry will decrease. As the amount of dissolved oxygen decreases, the fish start to die off because there's simply not enough oxygen in the pond to support all the fish. And they will die off until the population reaches a level that is sustainable. If you decrease the temperature of the solvent, you will increase the solubility. And again, we talked about fish with this one. I'm sorry, I got a degree in marine biology. That's the stuff that's in my head. Rainbow trout. Rainbow trout are a popular fish that people like to catch, but you can only catch them in the mountains. The reason why you can only catch them in the mountains and you don't see them down here in Lake Hartwell is because of the temperature of the water. Lake Hartwell is just too warm. That high temperature means there's not enough oxygen in that water for trout. Rainbow trout are a very muscular fish. They have a lot of red muscle, and red muscle needs a lot of oxygen. And there's just not enough oxygen in that lake for them. But if you go up to a cold mountain stream where the temperature is lower, then you'll find rainbow trout because that colder water will have more dissolved oxygen in it. And that extra oxygen allows those trout to survive. As far as pressure is concerned, the higher the pressure, the greater the solubility of the gas. So when pressure is high, you can dissolve more oxygen. When pressure is low, you dissolve less. And what we talked about here is trying to do athletic events in the Rocky Mountains. Whenever a football team heads out to Denver for an away game, they always get to Denver early in the week. They get to Denver early in the week so their athletes can get used to the lower pressure there. The altitude is much higher. It's a mile above sea level. And because the pressure is a lot lower there, there's a lot less oxygen that you can dissolve into your blood. So you breathe like you do normally at sea level, but you can't dissolve as much oxygen into your blood. So you tend to get winded much more quickly when you're in a place like Denver, when you're trying to do anything athletic anyways. They'll get there early because what your body will do to compensate is make more red blood cells. So your blood cells can carry more oxygen around. For a solid, the temperature effect is opposite. Increasing the temperature of the solvent will increase the amount you can dissolve. Decreasing the temperature will decrease the amount you can dissolve. And this is how you make a supersaturated solution. If you try to add sugar to cold, unsweet tea, you can never get it very sweet. And that's because it's cold. When it's cold, the solubility is low. You reach the limit really quickly. And all that extra sugar that you add to it just settles out to the bottom. If you want to make sweet tea, you add the sugar when the tea is hot. When the tea is hot, the solubility is high. So you can dissolve a lot more sugar. You dissolve the sugar when it's hot, then you allow it to cool down. As it cools down, the solubility will drop, but all that sugar will stay dissolved. And that is where supersaturated solutions come from. From there, we go into quantifying the strength of a solution. That's molarity, molality, and percent concentration. And then after that, the last thing that, the second last thing we're looking at, colligative properties of solution. We'll have acids and bases after that, but I won't post a video on that until we cover it.